As you learn the different groups of antibiotics and different types of antibiotics, it's really helpful to find a strategy or a structure for getting them organized in your head. I want to propose a strategy for you for organizing the different types that I think will really be helpful. You want to start with the mode of action. Okay, so there are several different ways that antibiotics can work, and if we can first group them in terms of how they inhibit bacteria in one form or another, then we can start to get them organized. So start with the mode of action, and then break them down into different classes. And these are really chemically defined classes that the organic chemists tell us: class 1, class 2, class 3, and so on. And then learn specific examples of drugs within each of those classes. What we're going to do here in this video is just walk through that process using the cell wall synthesis inhibitors as one of them. And then on your own time, I want you, as you're studying, to go through the other modes of action, the classes within those modes of actions, and then the different specific drugs. Take a minute now, pause this video, and make a list of all the main modes of antibiotic action that you can think of. Try to get as many as you can without opening up your textbook. Go ahead and click pause now. Okay, presumably you came up with a bunch of modes of action, even if some of them are just guesses. Here are the 5 main groups that most antibiotics fit into. First is inhibition of cell wall synthesis, and that's what we're going to model this video around. Second is protein synthesis inhibitors. Third are plasma membrane disruptors, nucleic acid synthesis inhibitors, and then folic acid synthesis inhibitors. And that's in particular one metabolic pathway, and we have a couple different drugs or classes of drugs that can knock out that particular pathway, a pathway that you and I don't have. So let's take some time and let's go through this structure using the cell wall synthesis inhibitors. So at the top, you see we've got inhibition of cell wall synthesis. I've broken it down into 3 classes. There's a 4th class in there that I should have put in that as you're studying you can put in. So we've got the penicillins, the cephalosporins, and then before we jump over to the polypeptide antibiotics, we should have the carbapenems in there. Those 3 groups, penicillins, cephalosporins, carbapenems, and there's another group called the monobactams that aren't as common, are what we call the beta-lactam antibiotics, and it's because they've got this beta-lactam ring that you see down in the bottom right-hand corner. It's a little square ring structure with 2 methyl groups, a nitrogen, and a carbonyl carbon. That beta-lactam ring is common to all of the beta-lactam drugs. They all have various activities and usefulnesses, and they're grouped together under the beta-lactam class or category. The polypeptide antibiotics are not beta-lactams. They're actually short polypeptides, a couple amino acids long, and we'll look at a couple examples there. And then we'll also look at a couple examples of cell wall synthesis inhibitors that are specific to the mycobacteria. So within penicillins, I've got some examples there. Penicillin G and V are the two natural forms of penicillin, and then we've modified those like crazy. We've modified them either to make them resistant to the beta-lactamases that the bacteria are using to protect themselves. We'll talk about those in a minute. Or to extend their spectrum of activity, because natural penicillin, G and V, is really only useful against the gram-positives. If we tweak a functional group here or there, make things like oxacillin and amoxicillin, all of a sudden we have broader spectra of activity, and we can start using them against some of the gram-negatives as well. So oxacillin, amoxicillin, methicillin, ampicillin, these are all different variations on the original penicillin G or V that have either a broader spectrum of activity or they're beta-lactamase resistant. Let's talk about those beta-lactamases. The first beta-lactamases were very limited in their activity. They could only work against the penicillins, and so they're also called penicillinases. They had a narrow spectrum. This is a bacterial enzyme that cleaves the beta-lactam ring and renders it inactive. You can see in this diagram here, you've got an intact penicillin on the left with its beta-lactam ring. The penicillinase snips it, creates something called penicilloic acid. That isn't as important as the fact that once that ring is cut, then the drug no longer interacts with the transpeptidase enzymes. And in fact, the beta-lactamases, these bacterial enzymes, are modified transpeptidases. Penicillins target the transpeptidases that are involved in cross-linking peptidoglycan, in particular cross-linking the glycan strands. And the transpeptidases are targeted, and the penicillinase or beta-lactamase is a modified, evolved transpeptidase that rather than cross-linking these glycan strands, it actually just cuts the drug and protects the bacteria. These are common in Staphylococcus and in many other species. So the penicillinases are narrow-spectrum beta-lactamases. We now are seeing more and more of what we call extended-spectrum beta-lactamases, ESBLs, that are bacterial enzymes that aren't just good against the penicillins, but they actually are effective against the cephalosporins and the carbapenems. So the cephalosporinases, like CTXM enzymes, can degrade or break both cephalosporin beta-lactam drugs as well as penicillin beta-lactam drugs. And the carbapenemases can cleave carbapenems, cephalosporins, and penicillins. And so the carbapenemases, fortunately, are very rare, but these are the most dangerous because they can wipe out virtually any of the beta-lactam drugs, which represents easily half of the drugs that we prescribe in the US today. Now, we fight the bacteria with beta-lactam drugs. They fight back with beta-lactamases to protect themselves. And so we fight back against the beta-lactamases with inhibitors. Potassium clavulanate, also called clavulanic acid, is a natural microbial compound. Acts as an inhibitor of beta-lactamases. If you look at the structure, you can see that there is a ring that is very similar to a beta-lactam ring, and therefore it is a competitive inhibitor of the penicillinases. Most often we see clavulanic acid combined with amoxicillin. That's under the trade name Augmentin. So the point here would be that if we suspect we've got gram-positive bacteria, or really I guess amoxicillin has a broader spectrum. So if we have, whatever our pathogen is, and we really want to use a penicillin type drug, we can add clavulanate to be sure that that there's not a beta-lactamase that's active that's going to render our drug inactive. There are some other beta-lactamase inhibitors you should be familiar with. In addition to clavulanic acid, there's also sulbactam and tazobactam, and you can see the most common forms of penicillins that these are used with. Now, some beta-lactamases are inhibitor resistant, right? This battle keeps going back and forth. So maybe we add sulbactam to our ampicillin, but the beta-lactamase that the bacterium is using is resistant to the sulbactam and is still able to cleave the ampicillin and survive the ampicillin. Turns out still, though, that the ESBLs that we talked about on the last slide are typically inhibitor sensitive, and so ESBLs combined with inhibitors are sometimes the way to go. I said that wrong. ESBLs, beta-lactams combined with inhibitors are sometimes the way to go, particularly if we suspect an ESBL. Okay, so let's shift from penicillins over to our cephalosporins. Cephalosporins are a little bit unique. They're very similar to penicillins. They have a beta-lactam ring. Penicillins are produced by Penicillium fungus. Cephalosporins are produced by Cephalosporium fungus, and it is a very similar and closely related fungus, in fact. We have multiple generations of cephalosporins, though. Keflex being a great example of a first generation. Cefaclor, second generation. Cefotaxime, third generation. Cefapime, fourth generation. And we're now on to fifth generation as of November 2015. We've got fifth generation cephalosporins. The idea is with these generations is we start with the original cephalosporin drug. We modify it so that it functions, and as we see resistance reach a certain point, we have to make new modifications and introduce a new generation of cephalosporin drugs. So it's a little bit scary that in just a matter of a couple of decades, we are already in our fifth generation where we're seeing increasing resistance to those earlier generations of cephalosporins. These are structurally similar to penicillin. They work in a very similar fashion. The penicillinases are ineffective against them, but they have analogous cephalosporinases. And the cephalosporinases are good against both cephalosporins and penicillins, so they have a broader spectrum of activity. The cephalosporins themselves have a naturally broader spectrum of inhibition than natural penicillins, and so there are some gram negatives that are naturally affected or susceptible to cephalosporins, where natural penicillin, G and V, is pretty ineffective against the gram-negatives. Here's an image of Keflex, cephalexin, broad spectrum, and you can see the beta-lactam ring in the center there. We're not going to talk about the carbapenems, but I want you to look into those on your own, find out a little bit about them. And here are the polypeptide antibiotics. These are teeny little proteins, essentially, bacitracin, colistin, polymyxin B, and vancomycin. Let's just highlight bacitracin and vancomycin. Bacitracin, the name comes from bacillus and Tracy, a little girl who had an infection with a bacillus species that was secreting a polypeptide. It was purified and found to have antimicrobial properties. And so bacillus infection in Tracy turned into bacitracin. This is a natural polypeptide, really just useful against gram-positives, and it's pretty toxic internally, so we typically just use it for cuts and abrasions. Vancomycin, also pretty toxic internally, as we've talked about in class. There's ototoxicity, there's renal toxicity, there's liver toxicity, and we have to really watch it carefully when we use vancomycin. This is also a natural polypeptide that is produced by Streptomyces species, also a very narrow spectrum, good pretty much just against the gram-positives. It's become our real go-to, really essential treatment for multi-drug resistant, difficult to treat MRSA infections. Now let's wrap this up by looking at some antimycobacterials. The two that are really just unique to the mycobacteria are isoniazid, abbreviated INH, I don't know where the H comes in. This is fully synthetic, inhibits the synthesis of mycolic acids, and ethambutol, which is also fully synthetic and prohibits the insertion of the mycolic acids into the cell wall. We often see them used in combination, and sometimes they're used in combination with streptomycin, and the three of them together seem to minimize the development of resistance. I will end here and leave you on this image. Why don't you take a few minutes to think through this concept check and see if you can answer this question. I hope you go through this video a few times, take lots of notes, compare it to our class notes, compare it to your textbook, and let me know if you have any questions.